Okay, we need to get into Newton's second law, and what makes it so that you can tell Newton's second law from Newton's first law is the fact that you have acceleration going on instead of moving at a constant speed. And how that's depicted in a free body diagram or a force diagram is that you have unbalanced forces, which means you can also think of this as the law where your net force is not equal to 0. Okay? So we're going to walk through the following situations. We have an object that's moving to the right and speeding up, an object moving to the right and slowing down, moving to the left and speeding up, and moving to the left and slowing down. Pay attention to patterns that you see, certain things that always point the same direction. This is very basic introduction to what we will deal with in more complicated situations. So here is a force diagram moving to the right and speeding up. All right, so our velocity vector and our acceleration are both pointing to the right. An appropriate force diagram to match this, let's give ourselves a mass to work with. All of this is considered, right now we're going to keep everything flat on a surface. All right, so our normal force and our frictional force would be, our normal force and our gravitational force would be equal to each other. And then in order for this to be true, your rightward force has to be higher than your leftward force, which really what that is 99% of the time is that our force applied is greater than our force of friction. And the force applied goes to the right. Okay? So moving to the right and slowing down, same mass, so same force of gravity and normal force. Except this time, if we have 20 newtons of force to the right, saying that's our force applied, the force of friction has to be higher. So let's make that 25 newtons. Okay. This would be an example of something that would be moving to the right and slowing down. So say you're pedaling a bike but not fast enough to overcome the friction of the road. So in this case, force of friction is greater than force applied, and force applied is to the right still. All right? So moving to the left and speeding up, maintaining our same mass. We have our same normal force and force applied. I'm just going to keep 20 newtons to the right, but in order to show that our velocity and our acceleration is going to the left, again, we'd have to have the left side have a higher Newton force. Okay? Now, this would typically, the most common way you would see this sort of thing, rather than necessarily friction slowing things down, because that would be an object moving to the right. This means your force applied now is to the left, and then it's still greater than your force of friction. That would probably be the simplest explanation for this one. And last example is moving to the left and slowing down. One 117.67 and keeping this at 20, slowing down while going to the left would mean that your rightward force has to win. All right, so I'll make that 15 newtons. Again, this would be more like your force of friction is greater than your force applied, but your force applied is going to the left. Just an example of how this would, a situation where this would apply. Okay, so if you notice, the velocity tends to go with the force applied, just in the examples that I'm giving you. All right, and then the acceleration, if you have been kind of picking up on this, matches your net force. Right, so I'm going to Now for each one, create a net force diagram, which looks a little bit different. All you do is include your net force vector. All the other vectors disappear. So add a net force vector to each diagram. So if you do this separately, the only vector drawn is the net force. Okay? So for this one, if you look back at your notes from before, move right and speed up, up and down the net force cancels out, left and right, you're left with 5 newtons to the right. All right? And those two point in the same direction. On this side, so moving to the right and slowing down, we end up with 5 newtons to the left. All right, our mass is still 12 kilograms. So, matches in direction. Then moving left and speeding up, again, you get 5 newtons to the left. The arrow of acceleration always matches the F-net arrow direction. And finally moving to the left and slowing down, we get 5 newtons to the right, winning out, or being the unbalanced net force, and those two arrows point to each other. All right? So you have to compare these to the pictures that we just went through and labeled with all of the possible forces. But hopefully a pattern you're picking on is that the direction of A, or acceleration, matches the direction of your net force. Okay? So, and this idea of the net force is required for figuring out Newton's second law, or using the equation F net equals m times a, or your net force is equal to the mass times the acceleration of the mass. All right, so if we're working with this mass, and we know it's moving at 5 newtons to the right, this was moving right and speeding up. Okay. If you wanted to say find the acceleration, you would have your 5 newtons of net force is equal to your 12 kilograms times your acceleration, or your acceleration would be 5 newtons divided by 12 kilograms, which ends up giving you 0.42 meters per second squared. And then since it's moving to the right, and key thing, speeding up, that makes this positive. Positive. Okay. So we will work more with finding the acceleration and other problems. Just some of the major patterns to notice was that the arrow of the acceleration always matched, like that direction always matched the direction of your F net. Your velocity vector, if it was going in the same direction as acceleration, that meant that you're increasing velocity, so you have positive acceleration. If it's going in the opposite direction, then you're slowing down, so that would be negative acceleration. Just some patterns to pick up on, and we'll work more with this in class.